Okay, so what I'm going to do is I'm going to move over to a short presentation which I prepared. This is what is there in your syllabus. Okay, there is a recapitulation of principles of green chemistry. There's a part on waste minimization techniques, and all of this is given fairly well in the Lancaster book, which is a introductory text to green chemistry. Then you have a part on catalysis and green chemistry. So we have phase transfer catalysts, biocatalysts, and photocatalysis, right? I think we'll be covering both 3.2.1 and 3.2.2 as of now. And I'll have some presentation like this prepared for you on 3.2.3 and 3.2.4, which involves some solvent specific green chemistry approach, uh, dealing with supercritical fluids like supercritical carbon dioxide, supercritical water, ionic liquid, and their use in catalysis and solvents. And the last part will be on how microwave and ultrasound result in enhancement of the rate of the reaction. So, okay, that particular part we'll cover in one subsection. Right now, we are just looking at 3.2.1 and 3.2.2. Okay. Now, to begin with, of course, these things are known to you that green chemistry is not a very old kind of a principle. It's a recent development in terms of sustainable chemistry, and that was realized because there is a boom in the chemical industry over time, and because of this boom, there was a lot of explicit exploitation of natural resources, and at the same time, without having any bearing on what we are building up into our environment. Okay, so that's the reason in one of the conventions in the UN Commission, it was discussed and the need was realized, whereby people said that there is a need that the present needs have to be met without compromising the ability of the future generations to meet their own needs. So that was in a way how green chemistry was conceptualized. And in the early 1990s, it was thanks to agency called US Environmental Protection Agency, EPA, which was led by Paul and Astas, which coined the phrase green chemistry. And they said that anything that leads to promotion of innovative chemical technologies which reduce or eliminate the use of hazardous substances in design, manufacture, or use of chemical products should come under the purview of green chemistry. And they, in their final documentation, which was prepared by Paul and Astas, which was co-authored by another author, they came out with 12 principles of green chemistry. And these 12 principles can, in brief, just be put together as prevention. Prevention is always better than trying to come out with some viable solution. There's a very important part on atom economy, and we will be discussing atom economy in quite some detail, because atom economy and environmental factor, or E factor, also called as effluent factor, are one of the main takeaways from the green chemistry principles. Okay. Then there is a part on less hazardous chemical synthesis. Wherever possible, we should try and involve less hazardous routes or less hazardous products should be synthesized at the end. You should be designing safer chemicals. Safer solvents and auxiliaries have to be used in any chemical process. The design has to be for energy efficiency. Use of renewable feedstock wherever possible should be practiced. There should be a reduce in derivatization. Like, I mean, you shouldn't have to involve protection, deprotection chemistry wherever necessary, because that just adds up to the number of steps. And as the number of steps go up, number of unit processes, unit operations also go up in a synthetic pathway, making the process in its entirety non-green. Okay. Okay, and catalysis is another very important green chemistry principle. Catalytic reagents are better than stoichiometric reagents. So that is another important design in terms of making the reaction or synthetic pathway green. Another thing is to design products for degradation. So the products by themselves should not be made to bioaccumulate or accumulate in the environment that doesn't undergo degradation. So they should have some mechanism that can allow them for getting degraded under the environmental kind of a scenario, right? And then there should be a real-time analysis for pollution prevention, so that you don't come out with this pollution as a factor being kind of what you can say, a part of a certain synthetic strategy after about 5 to 10 years of operating that particular synthetic pathway. So you should have some real-time mechanisms so that you can analyze as to what are the environmental risks, what are the environmental hazards that are happening real time. As the process is underway, you should be able to do some real-time monitoring. And the last principle is that there should be inherently safer chemistry so that accident prevention is exercised and practiced so that you don't have any accidents while you're practicing chemistry. So if you had to sum up all of these 12 principles of green chemistry in one image, earlier we used to be converting substrates into products, and the chemical process by itself, which involves a large amount of reagents, solvents, etc., used to end up leading to a large amount of waste, right? What we are trying to do by exercising principles of green chemistry is, can we do the same transformation of substrate into the product in such a way that a large amount of solvents, catalysts, etc. are used, which can help in recycling. And this recycling helps in making the waste considerably lesser as against what we used to practice in our conventional methods of synthesis, right? Okay, coming to the one of the fundamental, points of green chemistry, which is atom economy. We take a little closer look on atom economy. Atom economy is nothing but a ratio of the molecular mass of the desired product over molecular mass of all reactants. So we sum up the molecular masses of all reactants and put that in the denominator, and it's expressed as a percentage. So you multiply it by 100, so you get a value called as atom economy. It tells you how efficiently you are incorporating the atoms of the reactant into the desirable product. So that means lesser the byproducts that are formed in a certain synthetic pathway, the higher will be the atom economy of that pathway, synthetic pathway, right? Apart from this, you have other measures of reaction efficiency like yield and selectivity. So apart from yield and selectivity, which were conventionally looked at, I mean, it's not as if the earliest chemistry involved no mechanism to check on reaction efficiency. How did they check reaction efficiency? They used to check this overall yield of the process, right? And they used to check how selectively are you able to transform into the desirable product and not getting some byproducts in that synthetic pathway. So these were the only two measures of reaction efficiency. And after the principles of green chemistry were established, we added one more measure of reaction efficiency, which is nothing but the percentage atom economy. Okay, so whenever you're looking at any chemical pathway, you'll always come across these three parameters which are defined for a certain chemical process. There is conversion, there is yield, and there is selectivity, right? Now, what exactly do they mean, and are they replaceably to be used, or do they have some distinct place in the entire chemical synthesis is what is the question that we are asking. And when you look at conversion, a conversion is nothing but utilization of the raw material or the starting material in a certain synthetic pathway. To what degree has that happened will tell you something about the conversion in a certain synthetic pathway, right? So we are only testing whether the starting material has been consumed or not, without having any feedback on whether the desired product is the only one being formed or some other alternate products are being formed, right? And this is what we practice in the laboratory as well. If you remember your MSc Part 1 organic chemistry practicals, you used to find out whether your starting material has got completely consumed or not based on TLC. So what do? We spot our reactant, we spot the reaction mixture, and we see whether the reactant spot has got completely disappeared or not during the course of the reaction, right? And that would tell you whether 100% conversion has taken place or not. So how is percentage conversion defined? It is only defined as the amount of reactant that is converted divided by the amount of reactant that is supplied. So if you've supplied, say, 10 milligrams of the reactant while you've set up a reaction, and if all of the 10 milligrams has got converted, irrespective of what it has got converted to, you would say that the reaction is going with 100% conversion, right? So that is what conversion in an organic synthetic process means. Okay. However, you also need to know what is the degree of completion. Okay, because you may have more than one reactant as a part of a reaction pathway. Usually you don't have just one reactant, you may have more than one reactant reacting together to give you the product. So how do you check the degree of completion? The degree of completion is checked with respect to the limiting reactant, because the excess reactant is going to remain some amount of it unreacted after the end of the reaction. What is going to get consumed in its entirety would be the limiting reactant, right? So if the limiting reactant has got completely converted, so then you can say that your reaction has gone to 100% completion. That is what we mean by degree of completion. Okay. Now, how does it compare and contrast with yield, percentage yield? Percentage yield is more product specific. So there is a possibility, like say, for example, if I consider nitration of phenol, okay. Now, nitration of phenol will give you a mixture of orthonitro and paranitrophenol. But say, for example, if I'm only looking at paranitrophenol as my desirable product, okay, I don't want orthonitrophenol to form, or maybe that is the byproduct in my reaction that I can't avoid at this stage. But as of now, I'm looking specifically at paranitrophenol because that is desirable to be taken forward to para-aminophenol and finally to paracetamol, maybe in that particular pathway, if we are trying to probe, right? So in that case, what is going to happen? You may have converted all of phenol into its nitro derivative. So there may be 100% conversion of the reactant to the product. But in the 100% of the product that is formed, only says 55% would be the desirable product, which is paranitrophenol. And there could be 45% of orthonitrophenol that could have formed during the course of the reaction, right? So when you're trying to calculate percentage yield, you're only looking at how much of the product has formed, right? So if 55% of paranitrophenol is formed, then your percentage yield would reflect accordingly to give you only 55% of the desired yield, even if there has been 100% conversion from the starting material to the product, right? And how are yield and the concept of conversion related to one another? They are related to one another by this particular term called selectivity. How selectively you're doing a transformation will correlate the conversion with the yield. If your selectivity is very high, then all of the conversion that will take place will give you the desired yield of the product. If the selectivity is low, on the other hand, then not every converted starting material would give you the desired product. It may give you some byproducts or other products which you don't really need at the end of the synthetic pathway, right? And you define selectivity as a ratio of number of moles of desired product formed at the end of the reaction over the number of moles of undesired product formed at the end of the reaction, right? So these are your terms that have to be kept mutually exclusive and clear as to what do we mean by conversion, what do we mean by yield, and what do we mean by selectivity, right? Okay, continuing our discussion on atom economy. Atom economy can compensate for lower yields and selectivity. So as of now, we are looking at three very important measures of reaction efficiency. A reaction is called highly efficient if it goes with high percentage yield, one. It is called to be very efficient if it is going with high percentage of selectivity. And a new term that has got added on after the advent of green chemistry is a high degree of atom economy. So in some cases, a high degree of atom economy can compensate for a lower yield or selectivity. So the example that is given is, if you want to convert or if you want to synthesize maleic anhydride as the final product, you may do so either from benzene as the starting material, or you may do so from butene as the starting material, right? Now, when you start with benzene as your starting material, the formula weights are 78 for benzene and 4.5